before we move to the new material, we're going to start by repetition of some things associated with exponential functions and logarithms that we're going to use in this class quite a lot. Okay, so let's start with basics. If we have exponential expression in the form of a to the power of b, we call this part base, and we're going to do it right away. We're going to assume that a is either between 0 and 1, excluding 0 and 1, or somewhere between 1 and infinity. Of course, we would get very uninteresting cases if it would be 0 and 1. This is why we excluded them. And of course, there are always problems with when we need to take negative number to some power, especially if this power is somewhere between 0 and 1. This is why we exclude those cases right away. Okay, and let's refresh our memory about exponential, and of course this one, exponent, and this can be from negative infinity to infinity. So basically, our domain in this case are real numbers. Okay, so now let's review some of the rules on how to take a given number to some power. Okay, so a to the power negative 1, we remember the what the minus does is that we should take the reciprocal of a given function. Okay, and we can generalize it quite easily. If we have a to the power negative b, we have that this is 1 over a to the power of b. Okay, and then what do we do when we have a to the power 1 over c? Well, in this case, what we're supposed to do is to take c root out of a. Okay, and look, at this moment, we can start combining those rules, and we can get right away that a to the power b c is the same as a to the power of b and c root. Okay, finally, we can get the most complicated transformation, if we might say that, which is a to the power negative b over c, which gives us 1 over a to the power of b c root. Okay, what else do we need to know? Well, definitely we should mind two special cases, that a to the power of 1 is a, and that a to the power of a to the power of 0 is 1. But of course, this result holds if and only if we are excluding 0. This is a very important thing to remember. Okay, then we have some rules of operations with on expressions with exponents. The first one is that a to the power of b times a to the power of c is the same as a to the power of b plus c. The next one is natural extension of this one, that a to the power of b divided by a to the power of c is the same as a to the power of b minus c. Okay, then the last rule we need to know is that same as a to the power of c to the power of b. And of course, this can be simplified as a to the power b c. And actually, having this rule down, we can do a little bit more. We can actually prove that a to the power of 0 is 1. Because look, a to the power of 0 is the same as a to the power of b minus b. And based on that rule, we can conclude this is a to the power of b over a to the power of b. And this is 1, of course, as long as a is different than 0. Okay, I think this is not very complicated, and basically it covers everything we said about basic rules on exponents in our mathematics class. So now let's go to exponential function. So exponential function has the general form of, let's take specific form maybe first. Y equals b to the power of x with the same restrictions we made before. But now we use b like base, it makes more sense. The more general version of this function can be written as a b to the power c x. We're going to start with this function, and then we will slowly move to more and more complex version. Okay, so as an example, to begin with, let's just say that we've got a function y equals 2x. This is a good example because it's really, really easy to make numerical examples that will show us how this function actually works. And we're going to start with the table. Okay, so we've got x and y. And now, look, we will be interested in a couple of values of this function, especially when x is -4, -3, -2, -1, 0, 1, 2, 3, and 4. Okay, so now we can calculate what is happening to y as x changes. Okay, let's start actually with the middle. When x is 0, then of course y is simply 1. When x is 1, y is 2. And when x is 2, y is 4, then 8, then 16, and I hope at this moment you can recognize the pattern. The function is increasing, and it's actually increasing faster and faster. First by 1, then by 2, then by 4, then by 8. Oh, you can imagine the next increase will be by 16, and so forth. And now, what is happening when we move in the opposite direction? Well, when we move in the when x is -1, we get 1/2. When it's -2, it's 1/4. Then 1/8, and 1/16. Okay, so knowing all this gives us enough information to make a quite decent graph of this function. Okay, so here's x, here's y, 0, and we know that when x is 0, y is 1, and when y is 1, then we get 2. With x equals 2, we get 4. And then for 3, we would have 8, and so forth. So in general, this function looks like this. And look, what do we see over here? This function, starting from negative infinity, takes very, very tiny values, but the values are increasing. And look, they are increasing faster and faster and faster. But this fast increase we can actually see very well over here when we observe something that we call simply exponential growth. So even with the constant rate of growth, actually each consecutive increase is bigger and bigger and bigger. Okay, what is important here to remember is that also what is happening when we go to negative infinity. Look, we will be obtaining here lower and lower values. 1 over 16, 1 over 32, 1 over 64, 1 over 128, and so forth. The values will be decreasing, but they're of course never going to be 0. Well, the limit in infinity is 0, but generally we see that this function is bounded from below, and 0 is the point, is the value through which it will never go under. Okay, now let's make some transformations to this function, and let's see what's going to happen. Look, the first transformation, let's see what happens if instead of 2, we would have 1 over 2 to the power of x. But look, based on the exponential expressions, we've already seen in the previously, we see that we can easily transform this, because look, this is the same as 2 to the power negative x, right? Okay, so let's now make a new table for red y. We'll just say it's red. Okay, and let's look what will happen to the values this time. Okay, let's start with 0. Again, when x is 0, y is 1. But now, when x is 1, y is 1 over 2. Then 1 over 4, 1 over 8, and 1 over 16. When we go in the opposite direction, we actually see that here we will have 2, 4, 8, and 16. So look, if we want to draw this function properly, okay, let's hope it's going to look the way I planned it. Remember, I'm not a robot, so it's really hard for me to make a perfect graph. But what we get over here is a shape that is basically, well, that is exactly a mirror reflection of the previous function. So here, if we've got y equals 2x, and here we have y equals 1 over 2 to the power of x, we clearly see that if we can think about y, or vertical axis, as a mirror, and this mirror reflects what we've got on the other side. And look, so this function is declining, but look, it's declining slower and slower and slower. Here, we are getting closer and closer to x-axis, but we are never reaching it. Okay, so knowing this gives us a good starting point for further transformations of this of the exponential function. Okay, and now let's see what will happen over here if I'm going to say, we'll just say now with a blue color, and I will modify this function slightly. I'm going to add some a. In our case, this will be 3, so it's easy to calculate, times 2 to the power of x. Again, we can make a table that will show us what is happening. And look, basically, what we did is that we added 3 at front. So all we need to do, in order to obtain new values, is to take values of these functions that we already calculated and multiply each of them by 3. Okay, so what we will have here? 3 over 16, 3 over 8, 3 over 4, 3 over 2, 3, 6, 12, 24, and 48. Okay, so now, how should we draw this function? Well, look. This point now is going to be at 3. Now, when value of x is equal to 1, we are already at 6. When it's 2, it's 12. It's too far for me to draw. Now, moving in the other direction, look, now the value for negative 1 is equal to 1.5. Alright? Then it falls to, with negative 2, it falls to 3 over 4, so 0.75. And again it starts to fall, but we can see that it falls when we move to the left, it actually falls a little bit slower than this function. Actually, when we think about it, we can tell exactly how many times slower. Well, 3 times slower because it's here. Just as we had here, that this function was increasing 3 times faster. So what we get at the end is the function that actually increases 3 times faster. It has generally the same shape, but it's steeper. As you see here, it increases 3 times faster all over the curve. And very important thing, which is sometimes students like to forget about, but just say, remember, when we put 3 in front of the function, we also change the intercept of this function. So 2 things actually are changing here. One thing is the curvature of the function, because the function became steeper. Of course, if this number would be between 0 and 1, it would become flatter. But in this case, it became steeper. And the second thing is we moved the intercept. And remember, this movement in intercept is actually only a consequence of the change in the curvature of the entire function. Okay, and now let's consider the last possibility that we haven't covered. So here, what if now the function we are interested in is y equals 2 to the power 2x. So look, I just put a number over here in the exponent. So now any power that goes in here is multiplied by 2. Okay, so let's go back to the table and let's see what are we going to get this time. Okay, so now we have yellow y, and let's start over here. Well, 0, when x is 0, we still have 2 to the power of 0, it's still 1. Now, but when x is 1, the exponent is 2. So, it means that we are taking 2 to the power of 2, which gives us 4. And when we get 2, this turns, and when x is 2, this turns into 4. So we are raising x to the power of 4. 2 to the power of 4, which gives us 16. Then we've got 2 to the power of 6 with 3, which gives us now the curvature of the function has changed, but it's changed in a very different way from what we observed with the previous function. Because look, let's start from here. We are starting at 1. This is the common point for this and this function, but here the values are increasing, and they are increasing way faster than in the case of our base example. And over here, what is happening, we see that actually the values, when we move in that direction, are falling faster. So if we want to draw this, we will see something like this. And look, in this case, we've seen the curvature of the function changed significantly, and here the function is growing even the values of the function are increasing way faster. Now, which effect, if you ask, which effect is stronger? Putting a number up front or putting a number over here? Well, if you look at this graph, you would say, oh, definitely number 3. You see that the function lies everywhere higher. But, this is the illusion because we didn't have much more graphs. You can see this from the values. Look, over here, if we would go to the value number 2, actually, to be perfectly, if we would go to value number 2, here we have 6, here we have 4, right? Well, it should be here, right? But right with another value, we see that actually this function cuts through this one and it rises faster. Okay, so I think this covers all the basic information we had about exponential functions. In the next video, we will repeat logarithms. Thank you for your attention.